Okay, so in this video I'm going to have a look at the 2022-2023 Applied Maths Higher Level Sample Paper, question 4. So in part A1 we have, let's see, a ball is projected from a point on horizontal ground with initial speed u and at an angle alpha to the horizontal. The ball reaches a maximum height of h0 above the horizontal. Upon landing, the ball bounces with a maximum height of h1. The coefficient of restitution between the ball and the ground is e. Calculate h0 over h1. So we've got to calculate these two heights and then put h0 over h1. So first thing we're going to do is just let's have a look at the initial velocity. So it's going to look something like this. You've got a u here. We just resolved that into two vectors here. So this is an angle alpha here. So this is u cos alpha in the I direction, and this is u sine alpha here in the j direction. Now our initial velocity, u, let's call it u0, then can be written as u cos alpha in the I direction plus u sine alpha in the j direction. Now we want to find an expression for h0. So we know that at h0, the velocity in the y direction is going to be 0. So the velocity in the y direction is 0. So we're going to use the formula v squared is equal to u squared plus 2as, because we need to put in h0 here. So our velocity in the y direction is 0. Our initial velocity is in the y direction is u sine alpha. So that's u sine alpha, which we need to square, so we square that and square that. And then we've got minus 2g times h0. Okay, so let's just mess around with that until we get h0 on its own. And that'll give us, let's see, u squared sine squared alpha divided by 2g. So the next thing we've got to do is find an expression for h1. So in order to do that, we need to find the velocity after, or actually the velocity just before it bounces for the first time. And then we've got to incorporate the coefficient of restitution and so on. But in order to find the velocity just before it bounces, we need to find the time of the flight. So let's do that first. So the time of the first flight, then is just going to be, let's see, we're going to use s is equal to ut plus half a t squared. Now in this particular case we need the distance in the y direction to be 0. So remember, we're trying to find the time to the first bounce, and when the ball bounces the distance in the y direction is going to be 0. So our distance in the y direction here is 0. Our initial our velocity here is in the y direction is u sine alpha. Got to multiply that by t, and then we've got a half, it's actually minus a half g because g is acting downwards, and then we've got t squared here. Now if we divide across by t, we get 0 is equal to u sine alpha minus a half gt. So that'll give us our t here is equal to u sine alpha divided by, it's actually, when we bring it over and multiply by 2, it'll be 2 sine alpha, and then we've got to divide that by g. So this is our time to the first bounce. So to find the velocity then, we're going to use v is equal to u plus at. Now our velocity then in the y direction is u sine alpha again, u sine alpha. So we've got minus g, and then we've got the time here which we've just worked out, 2u sine alpha over g. This will give us our velocity. Our velocity, remember, in the y direction here. So u sine alpha, the g's here will cancel if you like, or divide to give you 1, and you've got minus 2u sine alpha. So that gives us u sine alpha minus 2u sine alpha is minus u sine alpha. Okay, so this is our velocity in the y direction. So our velocity in the y direction as it just before it bounces for the first time. Okay, so let's look at the second flight then. So this is a second flight, or just after it bounces. So we have the velocity then, the initial velocity, we'll call it U, just call it U1 there. This is going to be given as U cos alpha. Remember, this is the initial velocity in the x direction. That's not going to change throughout the whole process. So this is U cos alpha I. And then we have our velocity here in the y direction. Now this is going to be affected by our e here. Remember, the coefficient of restitution between the ball and the ground is e. So it's actually minus e, so we've got to multiply this by minus e here. So that becomes plus e times u sine alpha, and that's in the j direction. Okay, so the formula we're going to use now is v squared is equal to u squared plus 2as, and we know that at h1, the velocity in the y direction is going to be equal to 0. So let's just put in the information then into this formula. The velocity in the y direction here is going to be 0, so we've got 0 is equal to u squared, so the velocity in the y direction squared, which is this thing here, so that's going to be e squared u squared sine squared alpha plus 2as, so that's actually going to be minus 2g, and our distance is going to be h1. So if you mess around with that, then you just get h1 is equal to e squared u squared sine squared alpha all over 2g. So now we have h1 and we have h2, so we've just got to put one over the other, and that's our solution. So what we've got to do is work out h0 over h1. So we've got to work out h0 over h1. So our h0 was u squared sine squared alpha, u squared sine squared alpha all over 2g. And we've got to put that all over this thing here. So e squared u squared sine squared alpha, again all over 2g. So if we do that, we get u squared sine squared alpha over 2g multiplied by 2g. Remember, you got to flip this fraction upside down, multiply. That's e squared u squared sine squared alpha. So what will happen here, let me see, the 2g will cancel here, the u squareds will cancel, the sine squareds will cancel, and what you're effectively left with then is just simply 1 on the top and e squared on the bottom. Okay, and that's really it for this part of the question. Okay, so let's have a look at part 2. So the ball continues to bounce. Find an expression in terms of E and H0 for H5, the maximum height of the ball after it lands on the ground for the 5th time. Okay, so we know that H0 over H1 is equal to 1 over E squared, or you could write it like this, H0 as a ratio to H1, it's just going to be 1 is to E squared. So in other words, what we've got to do really is just multiply h0 by e squared to give us h1. So let's write some of these things down. Let's see, we're going to start with h1. That's just going to be e squared times h0. We've got to multiply the first height by e squared to give us the second height. So to find h2 then, we just do the same thing again. We're going to multiply e squared by e squared h0 by this thing here. So that's going to give us e to the power of 4 h0. Go again, so h3 then is just going to be equal to e squared times e to the power of 4 h0, which is e to the power of 6 h0. H4 then, again, is just going to be e squared times e to the power of 6 times h0, which is e to the power of 8 h0, and we have to go one more to find h5, so h5 is going to be e squared times e to the power of 8 times h0, which is e to the power of 10 times h0. So this is our answer here. Okay, so let's have a look at the next question. Two identical smooth spheres P and Q, each moving with speed u, collide obliquely. The line joining their centers at the point of impact is along the y-axis. Before the collision, the velocity of the sphere P makes an angle theta with the y-axis, and the velocity of sphere Q makes an angle theta with the j-axis, as shown in the diagram. The coefficient of restitution between the spheres is E, where E is greater than or equal to 0, less than or equal to 1. After the collision, sphere Q moves off parallel to the j-axis. Show that E is equal to tan theta minus 1 over tan theta plus 1. Okay, so what we're going to do first is let's just draw a few vector diagrams. So let's start with P. So P moves in this direction initially, and it has velocity u, angle theta here, so we're just going to draw the horizontal and vertical components. So this is going to be u cos theta, this here is going to be u sine theta. Afterwards, I think it's going to move in this direction here, let's say. So that's P. Let's look at Q then. Q moves in the opposite direction, generally this direction here. Theta is here, so I'm going to draw a vector out this way and another one up along here. So this here again is u, this actually is u sine theta, and here will be u cosine theta. Afterwards it moves off in this direction here, vertically upwards like this along the j-axis, so there's no I component. This is Q. Okay, so we have our diagram, so let's just write out the vectors. So beforehand, before impact, and after impact. Okay, so look at P first. The initial velocity of P is going to be u cos theta plus u sine theta times j, and then afterwards the velocity of P is going to be, now we don't know what the component in the I direction is going to be, so I'm just going to call it A, and then we have u sine theta because the j component is not going to change. Okay, so let's look at Q then. So we have the initial velocity of Q and the final velocity of Q. So the initial velocity of Q here is going to be minus u sine theta in the I direction, and then plus u cosine theta in the j direction. And afterwards then, because it goes along the j-axis, there's going to be no I component, so it's going to be 0I. So all we're really going to be left with here is plus u cosine theta j. Okay, so what we're going to do now is, we're going to use the principle of conservation of momentum, and then we're going to use Newton's law of restitution. We're going to combine the two, and hopefully that should get us where we need to go. So let's start all that. So principle of conservation of momentum is going to be m1 u1 plus m2 u2. That's going to be equal to m1 v1 plus m2 v2. Okay, so in our case then we need to look at m1 u1. So it's going to be m times u1 is going to be u cos theta. So it's going to be this here. Remember, we're only looking in the I direction here. So we're going to look at u cos theta here, and then m times minus u sine theta. That's going to be equal to m times the velocity afterwards. So again, it's going to be a here plus m times, it's going to be 0 here. Okay, so we're going to cancel all the m's. The masses of both spheres are the same. So we just really end up here with a is equal to u cosine theta minus u sine of theta. Okay, so this is our first equation that we're going to use. Okay, so really in this case, you know, the vector here, the velocity after impact for p is just going to be u cos theta minus u sine theta I plus u sine theta j. That's the velocity after impact for p. Okay, so the next thing we're going to do is look at Newton's law of restitution. So that just says that minus e is equal to the relative velocity afterwards. So it's v2 minus v1 over u2 minus u1. Now in our case, e, or minus e I should say, is going to be equal to 0 minus a, so the velocity afterwards. So it's just 0 minus a divided by the velocity before, so it's going to be this minus this here. So it's going to be minus u sine theta minus u cosine theta. Okay, so again here if we just simplify this, so we're going to multiply the left and right hand sides by minus 1, so we get e is equal to a over minus u sine theta minus u cosine theta. Okay, so we have an a here, so what I'm going to do is substitute this in for a, to give me an expression for e. So e then is just going to be equal to, e is going to be equal to u cos theta minus u sine theta. That's the first equation here. This was our second equation here. So that's going to be over minus u sine theta minus u cosine theta. Okay, so if we look at what we need to prove, we need to show that e is equal to tan theta minus 1 over tan theta plus 1. Now we've got cos's and sines here, so really what we've got to do is look at dividing by cosine. If we divide this by cosine, or u cosine, we'll get 1. If we divide this by cos, we'll get tan. If we divide this by cos, we'll get tan. And here we'll get 1. So that should sort it out for us, I think. So let's do that. So e then is just going to be equal to, so remember we're just going to divide by, actually what I'll do is divide by minus u cos theta to get rid of those u's as well. So let's do that. So here we're going to end up with minus 1 plus sine divided by cos is tan theta, and then here we're going to end up with just tan theta, and here plus, and then cos divided by cos is 1, so that's just going to be 1 here. If I just switch that around, we'll end up with tan theta minus 1 divided by tan theta plus 1, and that is it. That's what we had to derive. So that's it. Okay, so let's look at the next part of the question. If 25% of the sphere's total kinetic energy is lost during the collision, calculate theta and e. So I've written down the velocity of p and the velocity of q after impact. We're going to use that. Remember, we didn't know a initially, so we worked it out as this here. So we're going to use this here when we're working out the kinetic energy after impact. But let's look at the kinetic energy beforehand first. The kinetic energy before impact is just going to be half mu squared plus half mu squared, which is mu squared. This is because both spheres have mass m and they were both traveling with speed u before impact. So this is our total kinetic energy before impact. So let's look at the kinetic energy after impact. So in order to work out the kinetic energy after impact, we need to find the magnitude of P after impact and the magnitude of the velocity of Q after impact, and use those to work out the kinetic energy after impact. So let's do that first. So the first thing we need is the magnitude of the velocity of P after impact. So that's just going to be the square root of a squared plus b squared. In other words, the square root of this squared plus this squared here. So it's u cos theta minus u sine theta squared plus u sine theta squared. So let's just multiply this out. So we have, let's see, the square root of u squared cos squared theta minus 2u cos theta u sine theta plus u squared sine squared theta, and then out here we've got plus u squared sine squared theta. So let's just simplify this a little bit. We've got u squared cos squared theta. We have a minus 2u squared cos theta sine theta. I just multiplied these two u's here. And here we've got a u squared sine squared theta, u squared sine squared theta, so that's two of them. Okay, so that's the magnitude of the velocity of P after impact. Let's find the magnitude of the velocity of Q after impact. So that's just going to be the square root of 0 squared, and then we had 0 squared plus u cos theta squared here. So u cos theta squared. Okay, so that's just simply the square root of u squared cos squared theta, which is just u cos theta. Okay, so we have both our magnitudes of the velocities, and what we've got to do now is just work out the total kinetic energy afterwards. So the total kinetic energy after impact So that's just going to be half mv squared plus half mv squared. So let's do that. Okay, so total kinetic energy after impact then is going to be equal to half m times, I'll write the whole thing out here, so it's going to be the square root of u squared cos squared theta minus 2u squared cos theta sine theta plus 2u squared sine squared theta, and it's all squared. So that was the magnitude of the velocity of p. So now we've got to look at q then, so it's plus half m v squared, so that was u cos theta squared. Okay, so let's just try and simplify this entire thing then. So we have, I'm going to factorize out the half m first of all. Squaring this will just give us u squared cos squared theta minus 2u squared cos theta sine theta plus 2u squared sine squared theta. And out here then we'll just end up with u squared cos squared theta. It's this bit here squared. Now if you look at this, what we can actually do here is factorize out 2u squared, because we have a 2 here, a 2 here, and this here can be added to this one to give us 2u squared cos squared theta. So we can factorize out the 2, and also each term has a u squared. So let's do that. So 2 times a half is just going to give us 1. So that'll give me m. We're also factorizing out the u squareds. So I'll be left with cos squared theta minus cos theta sine theta plus sine squared theta. Remember, I've added this to this already, so that gave us 2 of those, and that's ended up here. Okay, so finally what I can do here now, I see within the bracket I've got a cos squared plus sine squared, which is 1. That'll give me 1 minus cos theta sine theta. Okay, so I have the total kinetic energy after impact, the total kinetic energy before impact. So what I can do now is just go ahead and look at the actual question, see how we're going to tackle that. So if we look back up here, it says 25% of the sphere's total kinetic energy is lost during the collision. Calculate theta and E. Now we have the kinetic energy before impact as being mu squared. So 25% of the sphere's total kinetic energy is lost. So we're going to lose 25% of mu squared. So that means there will be 75% left. So what I'm going to do is write down 75%, 0.75 of mu squared, our kinetic energy, total kinetic energy before impact. That should be equal to mu squared times 1 minus cos theta sine theta, our kinetic energy after impact. So that's my equation. From this I think I can work out theta, and from theta I can work out E. So let's do that. I'm going to just divide both sides by mu squared first, so that gives me 0.75 is equal to 1 minus cos theta sine theta. Bring over the 1, that'll give me minus 0.25 is equal to minus cos theta sine theta. Get rid of that minus, 0.25 is equal to cos theta sine theta. Now, what I can do here then is look at this part here. Now, I know from my trig identities in the tables that the sine of 2a is equal to 2 sine a cos a. And that's what I've got here. Well, I've got a sine a cos a anyway, if you like. So I don't have the 2. So what I might do is just multiply both sides by 2. That'll give me 0.5 here. 2, I'll put in the sine first here, actually, sine theta cos theta. So the right hand side will just change to sine 2 theta based on this here. Okay, so let's just look at this then to try and work out what theta is. Now if we look at our Argand diagram here, we need an angle that has a sine of plus 0.5. So sine is positive in the first quadrant, sine is positive in the second quadrant. We know that sine of 30 degrees will give us a half. So that means this here must be 30 degrees. And our reference angle here must also be 30 degrees, making our other angle here 150 degrees. So that just means then that 2 theta must equal, 30 degrees and 150 degrees, giving us finally our angle theta being 15 degrees and 75 degrees. So these are our thetas. Now, from a previous question, we've got to work out E. So from a previous question, we know that E is equal to tan of theta minus 1 over tan of theta plus 1. So let's just stick our 2 angles in there to work out E. So let's take theta is equal to 15 degrees. So theta is equal to 15 degrees. That means E is equal to tan of 15 degrees minus 1 over tan of 15 degrees plus 1. And also our theta can be 75 degrees. So that will give me E is equal to tan 75 degrees minus 1 over tan 75 degrees plus 1. On this side we'll end up with minus root 3 over 3. On this side we'll end up with root 3 over 3. So there are two e values. However, we know from the question that e has to be between 0 and 1. So e is greater than or equal to 0, less than or equal to 1. Therefore, theta has to be 75 degrees and e is equal to root 3 over 3. So we reject this side, if you like. Okay, so that's it for this question.